Hello everyone and welcome to this webinar. My name is Adel Banumi. I am a high-frequency application engineer with Ozen Engineering. In this presentation, I will talk about substrate integrated waveguide techniques for biosensor devices and how we can optimize them using Ansys HFSS. We are Ozen Engineering, an elite channel partner of Ansys. We have been named Ansys Channel Partner of the Year in 2015, 2018, and 2021. Our company specializes in Ansys software tools and provides best-in-class services for training, mentoring, consulting, and technical support. We'll start this presentation with a brief overview of the biosensing market and technologies, including what biosensing is, its applications, and the available types of biosensors. We'll then explore the SIW technology and talk about Ansys HFSS, a powerful simulation tool used for designing and optimizing SIW biosensors. Following this, we will review some of the SIW techniques used for biosensing applications. And finally, we will demonstrate some of the useful features for designing and optimizing a biosensor in Ansys HFSS. The biosensing market is rapidly growing and involves detecting and analyzing biological components and processes. Biosensors are devices that detect one or more biological components and can be used in medical diagnostics, environmental monitoring, and food safety. They provide a simple, fast, and sensitive means of detecting biological molecules and processes. Key technologies in the biosensing market include electrochemical sensors, optical sensors, and micro-electromechanical systems. The biosensing market has applications in healthcare, environmental monitoring, food safety, and other areas. For instance, biosensors can be used to detect pathogens in food, monitor environmental pollutants, or diagnose diseases by detecting specific biomarkers in body fluids. Their versatility has made them an important tool for many industries, and their use is expected to continue to expand. The biosensing market is driven by increasing demand for faster and more accurate diagnostic tools, as well as the development of new biosensing technologies. Researchers are constantly innovating and developing new biosensing techniques based on emerging technologies, which will continue to drive growth in the market. And today we are going to discuss one of these technologies that is relatively new and has shown great potential for biosensing applications and cost effectiveness. The Substrate Integrated Waveguide technology was first introduced in the early 2000s by Professor Kewu, a professor at the École Polytechnique de Montréal, and his team, in response to the growing demand for high performance and compact microwave and millimeter wave components. The SIW technology was developed as a solution to the limitations of traditional waveguide technology and has since found numerous applications in wireless communication systems, microwave sensors, and biosensors. The invention of the SIW technology has led to significant advancements in the field of microwave and millimeter wave electronics, enabling the development of new biosensing technologies. Its high performance properties make it well suited for use in biosensors where accuracy and sensitivity are critical. Here in this figure from the paper Substrate Integrated Transmission Lines Review and Applications, published in 2021 by Professors Kewu, Mauricio Pozzi, and Fonseca, we can see the evolving trend of publication records on SIW and its variants since its inception. The figure clearly shows a linear increase in the number of IEEE technical papers published each year over 15 years. Also, the publication trend for all journals and conferences, including both IEEE and non-IEEE contributions, seems to be increasing exponentially each year. Now, before we jump in and talk about substrate integrated waveguides, we need to first understand what a waveguide is, and more specifically, what a rectangular waveguide is. What you can see here in the bottom right-hand corner picture is a rectangular waveguide. It is a hollow metal tube that is designed to guide and confine electromagnetic waves at microwave frequencies. It has a rectangular cross section with one side being longer than the other, and the frequency range of operation depends on these dimensions. The waveguide is typically made of metal, such as copper or aluminum, and it is used to transmit microwave energy from one point to another. The advantage of rectangular waveguides is that they can handle high power levels, they have low loss, and they provide good shielding against electromagnetic interference. However, they are larger and heavier than other types of transmission lines and can be more difficult to manufacture and assemble. Substrate integrated waveguides are basically the planar form of rectangular waveguides. They are constructed using printed circuit board technology. SIWs are typically used to transmit electromagnetic waves at microwave and millimeter wave frequencies, and they offer advantages over other types of waveguides, such as smaller size, ease of integration with other components, and lower loss at high frequencies. Because of their planar structure, SIWs are easier to manufacture and can be integrated with other planar circuits on a PCB, making them a popular choice for many applications in microwave and millimeter wave engineering. Here you can see the E-field simulated using Ansys HFSS for both structures. This is for the fundamental mode, the TE10. Here's a summary of the advantages and disadvantages of both types. For rectangular waveguides, some of the advantages include low insertion loss, high quality factor, high power handling, and self-shielding. However, they also have some disadvantages such as high cost, high weight, complex manufacturing, and they are not easy to integrate. On the other hand, substrate integrated waveguides have lower cost and weight compared to rectangular waveguides, and they can be integrated with various passive and active components. They are also self-shielded, making them less susceptible to external interference. However, the insertion loss, quality factor, and power handling of substrate integrated waveguides may not be as high as that of classic rectangular waveguides. Now, let's dive deeper into substrate integrated waveguides and start with their topology. An SIW structure is composed of two metallic layers, typically made of copper. Between these metallic layers, we have a dielectric substrate material. The top and bottom layers are connected together using vias, which are usually cylindrical but can have any shape. These vias provide electrical continuity between the layers and allow the waveguide structure to be formed within the substrate material. The theory behind SIW structures is similar to that of rectangular waveguides. They have a cutoff frequency, which is the lowest frequency at which a particular mode can propagate through the waveguide. This cutoff frequency depends on the dimensions of the waveguide, the mode number, and the dielectric constant of the substrate. For the fundamental mode, TE10, the cutoff frequency can be calculated using this formula. But note that in SIWs, only TE modes can propagate because of the gaps between the vias, which serve as the sidewalls of the waveguide. The gaps would not allow for longitudinally oriented E-fields, and therefore TM modes do not exist. The design equations shown here are used to determine the equivalent width and length of an SIW. Although there are many articles on designing SIWs, simulations are extremely important to validate theory and optimize circuits before moving on to manufacturing. Some other types of substrate integrated waveguides are shown here. The first one is the half-mode SIW, which is a standard SIW cut in half to reduce the size. Here we talk about the TE050 mode instead of the TE10 mode. Second, we have air-filled SIWs, which replace the substrate with air as the dielectric material between the top and bottom metallic layers. This results in reduced loss and improved performance, but it increases the waveguide size compared to traditional SIWs. And we have slow-wave SIWs. They use a periodic structure of metal posts or walls to slow down the propagation speed of the electromagnetic waves. This is achieved by increasing the capacitance, and by slowing down the waves, we significantly reduce the size of the waveguide for a given cutoff frequency. So, if you're not familiar with Ansys HFSS, HFSS stands for High Frequency Structure Simulator. It is a 3D electromagnetic simulation software that is widely used for simulating high-frequency electromagnetic fields in a variety of applications, including antennas, microwave components, and radio frequency circuits. HFSS uses the finite element method to solve Maxwell's equations in the time domain or frequency domain. It can simulate the behavior of electromagnetic fields in complex geometries, including materials with varying properties, and it can also take into account the effects of losses and dispersion. HFSS is a powerful tool for designing and optimizing electromagnetic devices and systems. It provides a comprehensive set of simulation capabilities, including parametric analysis, optimization, and electromagnetic field visualization. Its accuracy due to the automatic adaptive meshing and flexibility make it a popular choice for researchers and engineers in the fields of electromagnetics and radio frequency engineering. HFSS has a very wide user base. We have signal and power integrity, automotive radar with SBR+, radio frequency and microwave filter design, co-site interference inside of large structures, SAR and biocompatibility for smartphones, ground penetrating radar in complex environments, and platform integration. HFSS is well suited for the design and optimization of substrate integrated waveguide biosensors for several reasons. With HFSS, we can accurately model SIW biosensors with complex geometries and materials. HFSS has optimization tools to improve biosensor performance and reduce size and cost. Advanced algorithms and parallel computing speed up simulations, allowing for quick evaluation of designs. We can integrate HFSS with other Ansys tools, and that enables multi-physics simulations and comprehensive analysis. And we have post-processing tools that are available for simulation, verification, and design validation. With all the benefits of using SIW technology, many microwave and millimeter wave components have been developed, published, and even patented. The number of scientific publications in which researchers develop SIW filters, antennas, amplifiers, and many other components using Ansys HFSS has been impressively increasing over the years. Here we can see some of the published SIW biosensors developed with HFSS. For instance, a microwave biochemical sensor based on a circular SIW approach for aqueous dielectric detection. This one was tested with simple mixtures of distilled water and glucose. In the second example, we have a microfluidic biosensor based on a cavity resonator. This has been demonstrated through analyzing the fibroblast cells from the lungs of a human subject. And the third example, which is a microfluidic substrate integrated interferometer, which has been demonstrated with buffer solutions, PBS and RPMI. What SIW biosensors are capable of includes detecting the presence and measuring the concentration of biomolecules in low concentrations. We can measure with SIW biosensors the concentration of certain liquids used in microbiology, such as glycerol, ethanol, and methanol. SIW biosensors have shown a good potential for early cancer detection and are currently being researched and developed for this application. Now that we have discussed substrate integrated waveguides and their different types, let's explore some techniques used in the development of SIW biosensors with the help of Ansys HFSS. The majority of SIW biosensors use the resonance technique due to the benefits it offers, such as high sensitivity and selectivity. Another technique used in the development of SIW biosensors is the use of transmission lines. By introducing phase shifts in the signal transmitted through the SIW, it is possible to detect changes in the dielectric constant of the material placed in the sensing region of the waveguide. This technique has the advantage of being relatively simple to implement and does not require any resonant structures, which can be beneficial in some applications. Here we have an example of a substrate integrated cavity resonator. So we have the basic SIW topology where we have the top and bottom metallic layers. Here we have a transition from microstrip to SIW. Here you can see a small opening where we inject the material under test. So by injecting the material under test in the structure, what we do is change the effective dielectric constant. And the resonant frequency depends on epsilon r, which here becomes epsilon effective. And by changing epsilon effective, we change the resonant frequency. So for different materials, we have a different frequency. And here you can see the E field for the TE101 mode. This type of structures have many advantages, such as the compact size and high quality factor, but they work at one frequency, and we cannot use lossy materials with this type of structures, because lossy materials destroy the quality factor and we will not be able to see the resonant frequency. In the case of SIW phase shifters, the principle is a little bit different, but the idea is the same. We have a sensitive region here where we inject the material under test. Here, when we change epsilon effective, we change the phase constant beta. And the phase phi is given by the phase constant beta multiplied by the length L. So by changing the effective dielectric constant, we change beta, and by changing beta, we change phi, the phase. And here you can see for different materials we have a different phase shift. Here you can see the E field for the TE10 mode, and you can see the interaction between the E field and the sensitive region. The advantage of this structure compared to the resonator is that the structure is broadband, and also if we use lossy materials, we'll still be able to see the phase shift. We can estimate the effective permittivity by the Maxwell-Garnett mixing rule given here. There are other mathematical methods that can be used to develop a model for biosensor or a sensor in general, such as curve fitting and regression methods, which are mathematical techniques used to analyze and model relationships between variables in a dataset. Here, for a given volume fraction, the effective permittivity depends on epsilon 1 and epsilon 2, where epsilon 1 is the relative dielectric constant of the used substrate, and epsilon 2 is the dielectric constant of the MUT, of the material under test. In the case of the resonator, when we inject a material, we change the effective dielectric constant, and that changes the frequency. For the phase shifter, when we inject something, that changes the effective dielectric constant, which changes the phase constant, and that changes the phase. When we talk about characterization or material measurement, we go the opposite way. So from the measured or simulated frequency, we can extract the effective dielectric constant using the Maxwell-Garnett mixing rule, and from that we can extract the dielectric constant of the MUT. Same thing goes for the phase shifter. From the phase we can find beta, and from beta we can extract the effective dielectric constant and then find the dielectric constant of the MUT. An additional technique for developing SIW biosensors using Ansys HFSS is radio frequency interferometry. Here we can see two different ways of implementing interferometers. An interferometer generally consists of two arms. Here we have a sensitive arm and a reference arm. We have a power divider and combiner. So we have a signal that comes here, and this is the input. We have a signal that splits here, and one half goes through the sensitive arm, the other half goes through the reference arm, then they combine here at the output level. The phase difference between the two arms is 180 degrees. So the arms are designed to have 180 degrees phase shift to ensure that we have a destructive interference. And this destructive interference, we can see it here as a frequency. So by injecting a material in this structure, the frequency shifts, and by retrieving the sample, the frequency goes back to its initial state. This structure was tested with buffer solutions, PBS and RPMI. Here we have another interferometer which is completely integrated. This one was tested with relative humidity measurement, and you can see that for different humidity levels we have different frequency. The advantage of this type of structures is their high sensitivity. Also, they simplify the phase measurement of the SIW phase shifter, and they reduce the measurement errors related to the dielectric properties variations by exploiting a differential approach. Here I have prepared a brief demonstration on Ansys HFSS using an SIW example to show some of the useful features when designing and optimizing a biosensor. Let's take a look at this example where we have a simple substrate integrated waveguide. Here in the project tree, we can see all the objects that were defined. You can see that we used a Rogers 4003 substrate. By right-clicking on it and selecting properties, we can view and edit materials from the extensive HFSS materials library. You might have noticed that we only have a substrate. We don't have the top and bottom metallic layers and also the vias. But if we go to the project manager and see under boundaries, here we have defined a boundary condition, perfect conductor. So if I zoom in, you can see that the top layer, the bottom layer, and also the vias are defined as perfect conductors. And that means that our SIW is complete. After adding a solution setup and running the simulation, we can go and view the results. So here, if I right-click on results, go to Create Model Solution Data Report, rectangular plot, select S11 and S21, click on New Report, we can see that our SIW is working properly. Also, if I go under Field Overlay, I can view the E-field and I can also animate it. Now I'll show you a way to reduce the runtime when you're dealing with a symmetrical SIW biosensor. And the key here is to use symmetry. So what we can do is select the entire structure. Well, first of all, let's make sure that we're selecting objects and not faces. So I'll press the O key on my keyboard. Now I select the entire structure. I go here and click on Split. Let's do it on the YZ plane, yes, and keep the negative side. Click OK. Now that we have half the structure, I'll press the F key on my keyboard to select the face. Now I select this face, I right click on it and go to Assign Boundary, Symmetry, Perfect H, and I have to edit port impedance multiplier and change it to a half. Click OK and OK. By doing that, we can reduce the runtime significantly. The last thing I want to show you here is how to run a parametric sweep to optimize the performance of your SIW biosensor. And let's assume that you have a substrate integrated waveguide and you have a functionalized region. In this case, it's this cylinder. To run the parametric sweep, what we do is we create a variable for this object. So I select the cylinder, I go here, and its properties, I go to radius and change it to a variable. Let's call it, for instance, radius. Okay, let's keep it as 1. Apply, okay. Now what we can do, let's go to Optometrics, right click on it, go to Add, Parametric, let's click on Add. Here we'll choose radius, our variable. Here you can see the nominal value of 1 millimeter as we defined it. So let's say I want to change it from 0.5 to 1.5 millimeters with a step of 0.1. I'll click on Add, OK, OK. Once it's done, you can go to View, Animate. Here, let's go to Parametric Setup and click here. As you can see, the radius of the sensitive region is changing accordingly. One more thing, under Optometrics, we can set up an optimization and sensitivity analysis to improve the overall performance of your SIW biosensor. To conclude, by using Ansys HFSS to design and optimize SIW biosensors, designers can improve the sensitivity, selectivity, and overall performance of their devices, which can enable a range of important biomedical and environmental sensing applications. HFSS is a powerful software tool for designing and optimizing SIW biosensors. It provides a comprehensive simulation environment and advanced design tools that enable designers to evaluate and optimize the performance of their SIW designs more accurately and efficiently than ever before. It helps reduce the time and cost associated with physical prototyping and testing of SIW biosensors by enabling designers to perform virtual experiments and iterate their designs quickly and efficiently. At Ozen Engineering, we provide technical support for a wide range of Ansys software tools that cover not only electronics, but also various other fields of physics. Although Ozen Engineering is headquartered in the heart of Silicon Valley, we collaborate with best-in-class companies worldwide to optimize product design performance and to improve product development processes for our clients wherever they are located and across a wide variety of industries. We have multiple offices located on both West and East Coast, as well as in Canada. Here's our contact information. If you'd like to get more information, please send us an email at info@ozeninc.com. If you are interested in Ansys software tools, you can send us an email at sales@ozeninc.com. For our existing clients, if you need support, you can email support@ozeninc.com and we will be happy to assist you. With that, I'd like to say thank you for your attention